Okay, so today we reach at the end the thermal universe. And here, of course, the basic idea is the following. Now, first of all, you could ask me immediately, how can it be thermal equilibrium? The universe is expanding, so in some sense it's not really thermal or thermal equilibrium. Indeed, we will see in a minute, this is actually only local thermal equilibrium, and it will be practically, the idea is that you have locally always a thermal state, because the interaction which keep the thermal equilibrium are always faster than the expansion of the universe. So the basic idea is to compare every rate with the velocity of the expansion of the universe, which is nothing else as the Hubble parameter, with the expansion rate. And then usually you have the two possibilities, of course, that the rate is much faster than the expansion of the universe, and then for whatever process A you are considering, which can be a scattering, a decay, a 2 to 3 scattering, whatever process you want. And in that case, the conclusion is usually that this process is in equilibrium. The second, of course, possibility is that you have another process B for which the rate is instead smaller or much smaller, so I don't need really much, but at least smaller than the age of the universe. In this case, of course, you cannot assume that you can keep up thermal equilibrium because the rate is smaller, and this means that you are out of equilibrium. Okay. Now, of course, you know, all of us knows that here we have a time dependence on the Hubble parameter. So things that can be, and in practice, the Hubble parameter is actually decreasing with time. So it goes like 1 over t. Okay. This means that you can have processes which are in equilibrium and go out of equilibrium, or vice versa, depending on what is the dependence on time of the rates. Okay? Usually also, we will see in a minute, in the case of thermodynamics, we don't like to use time as a variable. We tend to use the temperature. And this is connected to another assumption we will take for most of that case, the assumption that we have an adiabatic expansion of the universe. So generically, we assume that we have an adiabatic expansion. There are very few epochs in the history of the universe where we relax this condition. For example, reheating was one of these cases where we were actually producing, so we were starting with a state with 0 entropy practically, and we were producing a lot of entropy from the decay of the inflaton. And in that case, it was violating, if you want, entropy conservation, or the fact that you had an adiabatic expansion. And in that case, you cannot, of course, apply these relations that I am using now. And the adiabatic expansion means that the total entropy is conserved, but since we don't like to have actually global variables, we want to have actually the behavior of the entropy density. So we define the entropy density, and then we have in practice the relation that this one has to be 0. And then from this one, we can immediately read out how the entropy density changes with respect to the volume, and it's just nothing else as 1 over volume. So ds of S is equal to minus dV over V. So if you want, you can write this as a scale factor, and this is the usual minus 3 dA over A, or minus 3H dt. Okay? This means immediately that you can write down the behavior of the entropy. It goes like 1 over a cube. And this is practically one of the important relations. Now, of course, we would like to relate the entropy to the temperature. So how does the entropy depend on the temperature? And for that, we have to go back to thermodynamics. And in thermodynamics, we know that the entropy is nothing else as the density plus the pressure divided by the temperature. This is one relation you can obtain from the thermodynamic relations. So this one, it's actually quite useful because therefore we can immediately see, for example, once we have a particular pressure, and here we look in particular to the relativistic case, it will be clear later why. In the relativistic particle case, we know that the pressure is 1/3 of the density, so we have a direct relation. This is 4/3 the density divided by temperature. And we haven't then just to compute what is the density as a function of temperature and rescale, and you obtain the energy density. Sorry, the entropy density. We will actually do it later on. You can do the computation of ρ from kinetic theory, as we have already seen, and really compute the integral with a particular distribution function, in particular equilibrium distribution functions. So, well, let me do it now, and then we come back to this argument. So the basic idea and the basic quantity we will use is the phase space distribution. Distribution function. Which is for me a small f depending on x, p, and time. Notice that here I am using a slightly different terminology as what was used by Andrei Starinet a few days ago, in the sense that in this case this is a kind of density in the one particle phase space. You can really, so if you want, you can take the full 6n or n particle phase space and project in some sense the particles to the one particle phase space. And then of course in all little cube in the phase space, I will have a density of particles, okay? And this will be the number of particles which have this particular momentum and they are in this particular place. As usual, I will have the same problem as usual in thermodynamics, is the fact that if I have a cube, of course I have a discrete number because the number of particles is either 0, 1, 2, 3, but I will treat f, of course, as a continuous function, so with continuum values. And of course, as we will see later, I will use again the dilute limit, so in the sense that I will use the fact that the number of particles in the same little volume is actually small, okay, so that I can do some approximations later on. So this is in some sense f of x, p, t, dx, and dp is the number of particles in this phase space cell. Okay? And now the idea, of course, is to see how this is relating with, for example, the thermodynamic quantities. Now it should be clear that yes, since this is the number of particles with a particular momentum in a particular space, it is pretty easy to have the total number of particles in a particular space element, because I have just to integrate this. Okay, so I can define the number of particles so as usual in kinetic theory, I will have I can have a number of particles which in principle can depend on x and t, which is nothing else as the integration in the P with the appropriate factor of 2p and of course also the h bar if you want to keep track of that. And you have the integration of the distribution function. Okay? This is really a density in phase space, so if I integrate it in momento, I have the number of particles in a particular space x and time t. And so I can also compute the density. I have the same integral, but of course here I have to plug in the energy of the particle, which is in principle a function of p. Here I need of course to know what is the dispersion relation. And then I have x, p, and t. And of course I can also compute the pressure. Now what is the pressure? The pressure is usually connected to the kinetic energy of the particle. So what I have to integrate here is actually nothing else as the p square over the energy. Is there a factor of 2? Factor of 3 actually, yes. Times the distribution function. Okay? So in that sense you can interpret the thermodynamic properties as coming from the kinetic theory with a particular distribution function, and you can compute the number density of particles, the density of energy, the density of the pressure, in some sense pressure, and this is all depending on what is your distribution function in the phase space of one particle phase space. Now, of course, these integral in generically, you don't know what they are because you don't know what is the f, the phase space distribution function. But of course, there are some cases where we know what f is, in particular the equilibrium cases. So for the equilibrium cases, we can do all these integrals, and we can compute the number of particles, and also the energy density. So we can try to do it very briefly for relativistic species and non-relativistic species. So let me keep this one because I will need it later. So it should be clear that here the energy I have to plug in, for example, depends on the fact if I use a relativistic, I have a relativistic particle or a non-relativistic particle. So for example, in the case of relativistic, I have, as usual, E is the square root of p squared plus m squared. And actually, if I go in the ultra-relativistic regime, I can also approximate these as a p modulus plus the usual 1/2 m squared over p. Okay? And then it should be clear that we can do in practice the integral that we had before. And in particular, we can see immediately, for example, that if you want, you can see it already from the density of particle. In practice, it would be something like the integral in the 3p over 2 pi cube. And here you would have, for example, this expression, or the square root if you prefer, it's up to you. And then here I have to plug in a distribution function, for example, the equilibrium one. Of course, I could plug in Bose-Einstein distribution, Fermi-Dirac distribution, but what I will use actually is the Boltzmann distribution, since it is usually in the dilute limit both the Fermi-Dirac and the Bose-Einstein reduce to the Boltzmann distribution. So here you can write the usual e to the minus beta e, which is again the same square root of p squared plus m squared. Now from this formula, you can already see that if you do this integration, you can rescale all your momenta with the temperature, and you can take out a t to the 4th, okay, factor. And this one, therefore, should not be a surprise that if you do the computation, you get a pi square over 90 t to the 4. Okay? And this is practically in the limit of mass negligible. So, of course, here there is no dependence on mass because I am assuming that the mass is practically 0. Sorry, 30, not 90. I can't read anymore. I have to change my glasses, I have to admit. So, of course, what we need to do is also to add. So this one is actually for bosons. Sorry, I forgot, of course. This one is the computation for bosons. And it is the limit of the Boltzmann distribution. In principle, if you have fermions, you need an additional factor here. So this will be, so if you do the things more properly with the Bose Einstein, or the Fermi distribution, you find out that this one is either 1 for bosons or 7/8 for fermions. So it's not a big change, but it is a slight change in the case, a slight number change in the case of, yeah, and yes, so this one is the integral, for example, for the energy density. So already from this one, you notice that you have the energy density is depending on t to the 4th. So we can plug this in here directly. And what you obtain is something which go like t cubed. So you have the usual factor here, p square over 30. Some, yeah, the 90 comes from here actually, yeah, and the xi factor at t cubed. Okay? Now you can a bit generalize this formula because this one is for only one single species or one single degrees of freedom. In practice, usually you have many degrees of freedom, and also one species can have, for example, different spin degrees of freedom or internal degrees of freedom. And this, of course, you have also to take into account. So the generic formula for S is usually written in the form, yes, 2 pi square over 45 gs t cube, where gs is what counts all the degrees of freedom. And you can also, in principle, take into account also if you have different fluids or different particles with different temperatures. So the usual definition is that here you add this usual GB, which is the internal degrees of freedom, then T over the temperature of the species to the cube, plus the same thing for the fermions with the 7/8. Okay. Now, if you compute it, for example, for the standard model, you get something of the order 100, because there are quite a lot of degrees of freedom in the standard model.
So what's TBI and TBF?
Well, TBI, TBF are the temperature of the particular particle. So this is the generic formula you can use even if you would have, for example, the electron temperature to be different than the photon temperature.
But they can be temperature different if they don't interact, no?
Yes, of course. They have to be decoupled, and then in principle you could have different thermal baths with different temperatures. So that is the most generic. Of course, if everything has the same temperature, this factor is 1, and it doesn't matter.
So this should be the other way around, right? TD over T. So that the
sorry. Yes, you're correct. Sorry. Yeah. Yes.
So for example, in the case of neutrinos that we know they are decoupled, is this going to be the decoupling temperature?
Not the decoupling temperature. So in principle, this is the temperature which depends on time. But of course, the neutrino now have a different temperature than the photon now. So indeed, so they would both contribute to the entropy, but with different temperature. And this is exactly you correct it. You can write it with a single formula, but you have to consider this correction for the neutrinos or for the photon, depending on which temperature you take as a reference temperature. Often the reference temperature, of course, is the photon temperature, because this is what we can measure more easily. And therefore, everything, you have to see what all the other species have as a temperature in comparison to the photon temperature, for example.
And so far we only know neutrinos. Are decoupled, or are there any other?
Yes, at the moment we only know neutrinos, but in principle we could have also other particles, and also the dark matter is supposed to be decoupled. Of course, usually it's non-relativistic now, so you don't use this formula for that, but this is indeed usually the issue, that if you have any particle which is decoupled, you can take into account in any case with this expression. Okay, so this one was one case, and let me go directly to the other case, the non-relativistic. In the non-relativistic case, of course, the energy, you have to take the other limit, and then you have practically the mass plus 1/2 p square over m. So you have exactly the opposite limit. No, of course, I have c equal to 1 and all these kind of things, so you don't worry about factors of c. And therefore, you can see immediately that the density is, in this case, just a factor of m times the number density. Okay? And this means that in this case, I can just very easily compute the energy density from the number density. I just multiply by the mass. And of course, I have correction of order 1 over p square, but as long as it is really relativistic, this is a small correction, so it's not a big problem. Now, let me come to the pressure, therefore. Of course, in the pressure, you see immediately what happens with p square. If you are again in the relativistic regime, E and P are practically the same. So here what you get out is nothing else as the modulus of P divided by 3. But the modulus of P is also the energy. So this means this one again gives you exactly the relation you would expect, also from argument of for the photons. You have that the pressure, so in the relativistic case, the pressure, so, oh sorry, I have a P and I have a pressure, but okay, let me write it with a big P. This is nothing else as 1/3 of the density, okay? So you can see it immediately from the expression there. What happens to the pressure in the case of the non-relativistic case? Well, in that case, of course, the energy is practically the mass. So here we have a P square over mass. And this p square over mass is usually small, so again the pressure of a non-relativistic particle is practically 0, and we usually neglect it. Of course, if you want, you can compute it. So p square over the mass will be non-zero. So if you compute, of course, the integral will give you something of the order of the temperature. So you would have a pressure of the order of the temperature, and if the temperature is much smaller than the mass of the particle, this is of course suppressed again. Okay, so if you want, the pressure in this case is something like T over m, and therefore if you have a large m with respect to T, you have effectively 0 pressure, and this is what we took in our cosmological evolution. Okay, so this is all consistent. Now, of course, I want also to, yes, so let me go on with the issue about the entropy. So I have the entropy which goes like T cubed. So what happens then with the temperature? I know, as I said, that the total entropy is conserved, and therefore I can directly see that if I look at the change of the entropy, this will practically give me, or how the temperature changes with the expansion of the universe. So for an adiabatic expansion, I have practically that, well, I have two cases. First, I assume the number of degrees of freedom doesn't change. Okay, GS constant. This happens for periods of, so GS constant. So when do you change the number of degrees of freedom? Question.
If there's a phase transition.
Yes, if you have a phase transition, of course, but also there is another very simple reason why you should.
When they become non-relativistic?
Well, they become non-relativistic. So if I reach with a temperature 1 mass threshold, I have to drop those particles out from the relativistic degrees of freedom. Okay? That's why usually G star, I will show you or try to draw you a plot later. It's actually some kind more of step-like function. It's not really very continuous, even if effectively it is continuous, because of course the density is continuous and also the entropy is continuous. It's only that when you reach relativistic, from relativistic to non-relativistic, the entropy will practically drop. Okay, due to the factor we just discussed, that if you want, you have. So you have in that case that the density here will not be anymore the t to the 4th expression. Okay, so G is equal to constant. We can immediately see that then ds over s is nothing else as 3 dt over t. And this is equal to minus 3 dA over A, or if you want, minus 3h dt. And this is immediately telling us that the temperature, as long as you have the same degrees of freedom, in order to keep the entropy constant, the temperature has to drop like the scale factor. So this is exactly the relation. So you'd see that T goes like 1 over A. Okay? Or if you want, the entropy density satisfies this relation Okay, this one we will use later on. Okay, so it's diluted. This is exactly the dilution factor which we met also in the continuity equation, if you remember, for the case of pure non-relativistic matter with no pressure. And this was exactly the dilution by the volume. Okay, so this means that as long as we have the constant number of degrees of freedom, the temperature of the universe changes, but it changes with a velocity, I can read it out here, it's h. Okay, the change of the temperature goes like h. So it's again the Hubble with a minus sign because it decreases. So the expansion, the universe expands, the temperature decreases, but the rate of decrease is again h. So this is exactly the reason why initially I was comparing every rate also to h, because if I have any process which goes faster than the expansion of the universe, I can practically assume that the temperature is constant during that period, and compute the rates with constant temperature. And in that sense, I can forget about the fact that the temperature is changing. Okay? But otherwise, generically, I have a change in temperature. That means that, for example, the distribution of the particles will change in time. And in particular, for example, this is the famous example is, of course, the photons of the CMB. The photons CMB had a thermal distribution because they were in thermal equilibrium in the early universe. They decoupled at the time of the CMB decoupling. And from then on, they traveled freely, but they kept the same distribution in phase space. This means they got only redshifted due to the expansion of the universe. So if you want the temperature changed of the Planck distribution, and this is why now they are at 2.7 Kelvin instead. Earlier they were at much higher temperature, but the shape of the distribution is exactly the black body shape. Okay, it has been conserved because the expansion of the universe doesn't change the shape of the distribution, it just changes the temperature.
Logarithmic change, no?
Yes, sorry, logarithm. Yes, you're right, it's 1 over t. Yeah. Sorry. Okay. Now, of course, what happens if the number of degrees of freedom is not constant? Then, of course, I have to take into account also the change in number of degrees of freedom. This means this equation is not completely correct. I have to add a piece. And then usually the temperature changes more slowly because you have ds over s would be also dgs over gs plus 3 dt over t. So you see that if I bring it on the other side, then my dt over t would be equal to minus the A over A, and then I have a minus 1/3 dgs in gs over gs. Okay? Now, usually the change in degrees of freedom goes in the direction of reducing the degrees of freedom, exactly because a particle becomes non-relativistic and I can drop it. And then in that case, dgs is negative, so this one is a positive contribution. Then you see that the temperature which goes down slower than 1 over A. Okay? In principle, you could also think about cases where this is even changes sign. If you are able to change the degrees of freedom very, very much, then you could even, in some sense, again, reheat the universe. And this is exactly what happens in reheating, in that sense. We really change the number of degrees of freedom we have. And in that case, well, this formula doesn't apply there because we don't have entropy conservation. But in some sense, it's, you would have an additional term which gives you the change in entropy. Okay. So, but let me go back to the distribution functions. Yes, sorry, I promised you the plot of the change of degrees of freedom. Of course, we do not really know what happened to GS above the electroweak scale. In principle, there could be a lot of particles there that we don't know about. But if you consider the latest epoch of expansion of the universe, we do know more or less how it goes. And this is the plot, depending on the temperature, GeV. This is the number of degrees of freedom. Actually, sorry, I forgot. In principle, you can define a similar thing as the G for the density as well, okay? Because also for the density, you have to sum up over all particles. They are not exactly equal because, as you saw, the correction I had here was a T over TB over T cubed. If you write the same formula for the case of the energy density, you would have TB over T to the 4th power in order to correct for a different temperature. That's why in cosmology we keep them separate. But in if in the case where everything is at the same temperature, they are actually related to each other because the density and the pressure, the density, energy density and the entropy density are related by the thermodynamics expression I gave you. Okay, so if all the species have the same temperature, then the relation which is valid for one species is valid for all. But so generically, you could have two G's. But as I said, in the early time, they are actually equal. And the behavior starts at about 100 for the standard model. Here we will have a 10. It's a logarithmic scale. And we have so we have a relatively constant behavior. Then we have really a drop. This is the QCD phase transition. Then we have for a while again a relatively constant behavior, and then we have another drop when there is the annihilation of the plus E minus. And now, if you want, the G and the G star are not exactly equal, exactly because the neutrinos have a different temperature than the photons, okay? So if you want the G and G star here are not exactly, you would have another, we have a G, I remember G S is a bit larger than G for the density, G rho. And here the temperature, of course, here is the temperature of the 10 to the minus 1. This one is a 1, and then of course the decoupling of the here happens as something like 10 to the minus 4 GeV temperature. Okay, but as you see, two typical numbers for G star or GS or G rho are either 100 at very early time, or in this plateau it is approximately 10. It is the case where there is the first generation in some sense around. It's the case also what is important for the nucleosynthesis. And then now, of course, we have as relativistic degrees of freedom only the photons and the neutrinos. So G is pretty small. Okay, it's a factor of a few.
And there is no electroweak transition? Or?
Well, I did not plot it. In principle, of course, if you had, you could think that you had additional degrees of freedom, but in that sense, the degrees of freedom, as we heard, in the electroweak phase transition don't really change. So you would not expect really a jump in the G star. And also, as you see, I am plotting, this temperature is about 10 to the, well, here in the plot is written 10 to the 3, but keep it with a grain of salt what happens at high temperature, because of course we don't know if we had other particles. So far we haven't found any other particle below 1 TeV, but of course if there would be some more particle, you would have to take them into account if they are in thermal equilibrium. Okay, so here, of course, as I said, is the standard model particle content. Okay, so in practice, if we add more particles, then you have to change it. Okay, so let me go back then to the expressions for the. Sorry, I also practically did not discuss very much about the entropy for non-relativistic species. Why is the entropy for non-relativistic species negligible? Because you have the entropy of a non-relativistic species will be again rho over T, because you don't have any pressure. And then if you put in the number, this would be again, as I said, m, the number of particles dividing the temperature. And if you plug in, for example, the number of particles, whether by a Boltzmann distribution, what you obtain here is that the number of particles is exponentially suppressed. Okay? So you find, therefore, that here you have a G, number of degrees of freedom of the particle, m, you have a m over T, 2 pi also, to the 3/2, and the exponential of minus m minus mu over T. So here I am adding also a chemical potential, because of course in the case you have a conserved charge and you cannot get rid of it with in another particle, then of course the number of particles is practically fixed by the charge conservation. Okay? But generically, especially if you don't have a conserved charge for the particle, then this is suppressed by e to the minus m over t, which is a tiny number as long as m is larger than t. And this means that in principle, we practically say that the non-relativistic degrees of freedom has 0 entropy, and we forget about them for the entropy discussion. Okay. Well, of course, as I said, if you want, I can write down also the distribution functions f in equilibrium are usually the Bose or Fermi distributions. So they are, in this case, I count the number of internal degrees of freedom separately. So I have a 1 divided e to the beta e minus mu plus or minus 1 as usual. Okay? And then, of course, in the limit where you go to the case where you have, when you are sufficiently diluted, this goes like more or less the Boltzmann distribution, as I said. Notice that here I am introducing the chemical potential as a chemical potential in the relativistic case. This means that it's really connected to a conserved charge. So, for example, you can have a chemical potential for the baryon number, for the lepton number if it is conserved. You can have a chemical potential for, in principle, also for the electromagnetic charge. But you do not have or at least you don't have the single particle, of course, chemical potentials. If you go non-relativistic, then of course also the number of particles for each species is conserved, and then you would have additional, or you could define a chemical potential for every particle species. But where you are relativistic, you have, for example, just a few chemical potentials, and every particle which has a particular charge will in some sense have a contribution on the chemical potential from the same chemical potential. Okay, now let me go to the formula for the density of radiation, which I didn't write explicitly. I write it only for one species. You can write it for the general species, and it is similarly, you define this G rho factor, where G rho is exactly defined in a similar way to the GS. So it is the sum over bosons and fermions of the internal degrees of freedom of the boson and fermion, and you have again a factor of T boson divided T to the 4th power, and for the fermions a factor of 7/8 and GF TF over T to the 4th power. Now, the good news is that this expression, if I am in the early epoch of the universe where radiation is dominated the energy density, I can plug this expression also inside the Hubble parameter. And I obtain the famous formula that the Hubble parameter square, we have this usual A pi Gn over 3, and then we multiply by the energy density in radiation. So P square over 30 G rho T to the 4. So in that sense, I have also dependence on T from the Hubble parameter. It gives me that the Hubble of T is nothing else as square root of 8 pi cube Gn over 90, and there is also a G rho, and I have a T square. Okay. Now, if you want, you can also, often is done that the 8 pi Gn is 1 over m Planck, and then you can take out also 1 over m Planck squared. So you can take also out 1 over m Planck. So I can do that and cancel here the Gn. Okay? This is a bit more convenient, so you know at what scale I am comparing to. Okay? The Hubble is always the temperature divided by m Planck times the temperature. And since T over m Planck is usually much smaller than 1, this means that the Hubble parameter is usually quite smaller than the temperature of the bath. Okay, and of course you can use this relation also. Since we know how the Hubble parameter changes during radiation dominance, it is equal to the Hubble parameter is 1 over 2 times the time. We can also invert to this relation to see how the times relates with the temperature and vice versa. Okay? I will not write it explicitly, but this is exactly what we need, because later on we will write equations as a function of temperature and not as a function of time. Okay. Now, in this equilibrium setting, what can you discuss? Well, one of the first things people discussed and worked out was, for example, nucleosynthesis. So, we can shortly try to discuss what are the processes in nucleosynthesis. And now, nucleosynthesis is one of the earliest epoch, actually is the earliest epoch we can really get information on, because of course the CMB decoupling happened much later. The Big Bang nucleosynthesis happens at about a temperature 1 MeV. The decoupling of the photons happens at the temperature around 1 electron volt. So this means that you have a 10 to the 6 difference in the temperature in the two cases, and this is in practically the earliest information we have if we will not be able in the future to get more information from gravitational waves or some other informations, but at the moment this is really our earliest probe. And we know that at that time we were in thermal equilibrium, okay? So before BBN, we had that the electroweak interaction was in equilibrium. For example, we can have we had, of course, one process. For example, for the neutrino, we could have E plus E minus going into neutrino and antineutrino. Okay? Or we could also have the scattering of the electron with the neutrinos. Well, of course, you could have E plus or minus, you don't care. And also the neutrino can be antineutrino. Also here, it's an elastic scattering. And in principle, you can try to compute what is the energy or the temperature at which this decoupled. And the condition is, again, that your Hubble parameter will be of the same order as the rate of the process. Now, luckily, we can do the computation pretty quickly, because we can use the Fermi theory, okay? We are at temperature which are relatively low, so we do not really care that the W or the Z are on shell. I mean, they are on shell and they are just to give you an effective operator in the low energy theory. So you can write down the cross section of the process as a alpha square electroweak divided the mass, for example, of the Z. Let me take only the channel of the Z. Of course, you can take also the W. It's more or less the same mass in my order or approximation. And then, of course, usually you know that since we have a non-normalizable theory, this is usually proportional to an energy or to the S variable, Maldesov variable. And in this case, of course, what should I have to plug in here? Well, in this case, of course, as long as this particle have a mass which is much smaller than the temperature, the right scale to use here is just the temperature scale, because that is the scale of the kinetic energy that the particle have. So this one is alpha square electroweak mz to the fourth t square. Of course, if you want the rate of the interaction, it's not enough to have the cross section. The rate is the rate for one particle, so you have to multiply it with the number density of the second particle. So if you want to compute the rate of the electroweak process, this would be the cross section times the number density. Of course, here I don't care neutrinos or electrons, they are practically the same because I can neglect the mass. So it's just a relativistic number density, and I will take the value of in equilibrium. And therefore, in equilibrium, this is actually something which, well, I didn't compute it, but if you compute it, you find that it's something proportional to t cubed, okay, instead of t to the fourth, because you have 1 power less of the energy when you do the integral, and this gives you a t cubed. So if you plug in the numbers here, you get something which is an alpha square w over m to the fourth z t to the fifth. And this one you have to compare with the Hubble parameter, which I just erased there, which is the factors which I had before. Okay, I can write it as a pi over 30, a g star over 10, a t square over m Planck. So this is the Hubble parameter of t. And I'm trying to find the temperature at which the rate is equal to the Hubble. This will be my decoupling temperature approximately. And you see immediately here you have a dependence on the temperature, which is t to the fifth. That means due to the fact that it's a non-normalizable interaction, the rate is going down very quickly with the temperature. Instead, the Hubble parameter is going down much, much more slowly. This means we will have a crossing of the two, and indeed, this you can simply solve, and you get a temperature for the decoupling which is of the order, well, it's mz to the 4th divided by alpha square electroweak m Planck to the 1/3. And here, of course, you can plug in numbers. And if you plug in number, what you get out is a 3 MeV. Now, this one was a little bit back of the envelope computation. It says I dropped some factors, etc. You can do the, and of course, I consider only this process. In principle, there could be also other processes around. For example, you could have, well, we'll see it in a minute. Also, the nucleons can be involved. And what actually you go to consider in reality, you get something more than 1.5 MeV. If you do the computation a bit properly with also Boltzmann equation and so on. So you see immediately that this is the temperature at which you decouple the neutrinos in practice. Of course, for the decoupling of the neutrino, there is another process which is important, which is the scattering, or the the, if you want, the decay of the neutron or the inverse decay, and also the scattering of neutron and proton. And this is the one other important process, which I think it's the last thing I will discuss, because otherwise I don't get to the Boltzmann equation. So you have, in principle, of course, another electroweak process is the fact that you can have E minus with a proton going into a neutron and a neutrino. Or you can have, of course, the other proton plus neutrino with not plus and E plus. Okay? And these processes is exactly what keeps in equilibrium the protons with the neutrons. And there is only again the interaction through the Fermi coupling, which gives you this type of processes. So it's not a surprise that they do the coupling at more or less the same temperature as the others. I'm not going to do the computation here. The only thing is that as long as you keep this in equilibrium, you can actually predict what is the number of neutron with respect to the number of protons, just from equilibrium consideration. And this is the following formula, which is just connected to take the Boltzmann distribution for the two particles. And you have an exponential of minus the difference in the masses. And then you have, of course, in principle, also a dependence on the chemical potentials. So this means, for example, you can see immediately that this number, it will depend. If I have overdensity, or no net lepton number, for example, and the chemical potentials of the neutrino or the electron would be much larger than the baryon number chemical potential, here I could actually change the number of neutrons versus number of protons. Usually the assumption is these numbers are the same numbers as the chemical potential of the baryon, assuming that the lepton number is more or less the same as the baryon number in the universe. And then those numbers are really tiny. So what you can have, or what you have, is that this is nothing else as dependent only on the mass difference between the neutron and the proton. And that is exactly the equilibrium consideration. Of course, the neutron is slightly heavier than the proton, so you have actually a suppression on the number of neutrons. If you compute Q, which is the delta M, is on the MeV also scale. So you see again that if you decouple at around the MeV scale, you will decouple with a sufficiently large or a not negligible number of neutrons. Actually, what happens is that this one is of the order 0.2 if you plug in the equilibrium number with the neutrino decoupling temperature. Okay? Notice that it could have been completely different. The difference from masses could have been much smaller, for example, or much larger. And then we would have a completely different ratio of helium to hydrogen in the universe, okay? Because this one is at the end what sets the number of helium to hydrogen. And of course we will have to, one has to add the decay of the neutron, so until you really start nucleosynthesis there is still time for some of the neutron to decay away, and this number is a little bit reduced, but nevertheless this is the main effect, that this relation here, which in some sense sets the decoupling of the neutrino, sets the temperature of decoupling, and sets also therefore the ratio of the neutron to proton. And this in some sense is one way why we can know more or less how fast the universe was expanding during nucleosynthesis, okay? And we can also know in that sense also if there's something funny is going on with the lepton numbers, because these would modify the neutron to proton ratio and then also modify the density of helium. So what happens later in the nucleosynthesis? In nucleosynthesis happens then, of course, that you have to bring neutron and proton together to form nuclei. And usually the idea is the neutron get all captured practically in helium with small fraction of other elements. But before you're really able to do that, there is actually another important step that it's a bit interesting, is the fact that you have to overcome the fact that you have a lot of photons in the universe. So the first step of nucleosynthesis is actually the fact that you have to produce deuterium. Deuterium is the simplest light element. It's a proton and a neutron will go into a deuterium plus a photon. Okay? Notice that the deuterium bounding energy is pretty low. And so this gamma will be not very energetic, but of course the problem is you don't have only this process, you have also the inverse process. And as long as you are in equilibrium, the number of photons here in this process, the number of photons present in the universe is much larger than the number of protons and neutrons. Because we have a baryon number which is 10 to the minus 10 with comparison to the photon number. This means that actually it's very difficult to produce deuterium, because even if you produce it, immediately there will be a photon coming and destroying the deuterium. This is usually called the Deuterium Bottleneck, and this is one reason why we actually, you have the decoupling of the neutrino as 1 MeV, but you start really do nucleosynthesis a little bit later, okay, at temperature. So this process, you can again compute the rate, and you can see that it decouples actually at a temperature of 0.06 MeV. So if you want, this keeps low deuterium until a temperature of the order of 0.06 MeV. And this you can again solve just by equilibrium considerations, by computing again the number of photons over the number of deuterium states. And you find that you have again this 10 to the 10 factor due to the asymmetry of the baryon asymmetry, if you want. You have a 1 over the density of the fraction of deuterium. And then you have the binding energy of the deuterium over the temperature square, and again the Boltzmann factor. So I'm writing here the photon number over the deuterium number. This means that's why I have a large number. Perhaps I should have actually given you the opposite. There it would have been clearer. But that means that the deuterium number remains small until these exponential factors start to win against this 10 to the 10. This means, as I say that you have to wait quite a long time in order to start really to produce deuterium. And then when you produce deuterium, you do produce also helium and so on, the other elements. And I don't have time actually to go through it. Of course, after you go at lower temperature, you start to have the region where the equilibrium arguments are not more enough to really give you a reliable result. And then, of course, people solve, of course, the problem numerically using the usual Boltzmann equation and the numerical solutions for nuclei.
Sorry, what was X of D?
X of D is the density of deuterium in units of the density of protons, if I remember correctly, or no, it's the number density of deuterium divided the sum over all the baryon densities. So n proton plus n neutron plus all the possible way you can distribute the baryon number if you want. Okay, so this one is the most I can say about nucleosynthesis. I wanted just to mention, because as I said, it's one of our earliest probes, and it is really also kind of proof that we were in thermal equilibrium at that temperature. And this is usually also a constraint in your model building. You need to build also your reheating model or whatever in such a way that you are in thermal equilibrium a little bit earlier than nucleosynthesis, so with a few MeV temperatures, in order to have the usual picture of producing the light elements from a thermal equilibrium state. But let me come now to the other issue. How do you solve the case where you are not in thermal equilibrium? And of course, even for that, we have to take again the help of kinetic theory. So we write down a Boltzmann equation for the species we are interested in. The good news is that usually we do not have the case where everything is out of equilibrium, okay? We usually follow one distribution function for a particular particle which goes out of equilibrium, and we can assume often that the rest of the particles are in equilibrium, okay? So I will try to write the Boltzmann equation for that case. So Boltzmann equation. Now, there is another issue which I forgot to mention. Of course, if you have a thermal equilibrium has usually two different types of equilibriums. There is the kinetic equilibrium and there is the chemical equilibrium. I hope you are all familiar with it. So the kinetic equilibrium means that distribution in velocities has the shape of a thermal distribution. The chemical equilibrium means that the number of particles is the equilibrium number, okay? These two things are disentangled because one depends on inelastic scatterings, for example. The other one depends only on elastic processes. So you could have cases where the chemical equilibrium is violated, but the kinetic equilibrium is still kept, and vice versa. And indeed, this is the case we will look at. We will write first the generic Boltzmann equation, but then we will specialize in the case where what is the important equilibrium which is violated is the chemical equilibrium. Okay? And this is the typical case of WIMP. Okay, so let me go to the Boltzmann equation generically. So we have already heard about it. This is nothing else as an equation of motion for our distribution function, which I can write as a Liouville operator for the distribution function. And the Liouville operator will be equal to a collision operator. Now, the collision operator, as we heard already 2 days ago, is in principle depending on a kind of two-point function. But in practice, what I will do here, I will again approximate this in the dilute limit that the two-point function is nothing else as the product of the one-point functions. So this means that this will depend again on f. And in principle, other distribution functions, so a second distribution function if you want, which will be in equilibrium, and I will write it in the integral. It's not written explicitly in the collision integral. Now, the Liouville operator we already saw. The only change we have to make is that we are in an expanding universe, so we have to add also the non-trivial derivatives and covariant derivatives. This generically you would write, therefore, the Liouville operator if you write it for GR. It is nothing else as P alpha d in d x alpha minus you have a Christoffel symbol. So you have the Christoffel symbol alpha, beta, gamma, and then you have a p beta, p gamma, the d in d, p alpha. Okay? So the first part is pretty clear, but the second part is non-trivial if you have a curved spacetime. And in our case, we have actually to take track only a few of the gamma. So we have in the non-zero gammas are the gamma 0 I, which is actually minus h GII. And then we have the gamma I0I, which is the gamma I0. And this is nothing else as the Hubble parameter. So if you then rewrite everything, you find that the Liouville operator, it's therefore equal to, you have a P0 D0, you have a P gradient, you have a minus h p square for the II component dp0, and then you have the other, which is 2h p0 p d in dp. Okay, this one is the generic case, but of course we had assumed, we had taken some assumption in cosmology, in particular isotropy and homogeneity. This means that also our distribution function has to satisfy the same at least at zero order. Of course, again, we can always write also f plus a fluctuation, which is space dependent. But generically, I would say that, as I said, homogeneity and isotropy imply that at zero order, at least, the distribution function can always that cannot depend on space. It can only depend on the modulus of the momentum and on time. Okay? Because if you would have, otherwise the vector p would also be something which is not isotropic, and the dependence on x, of course, comes from the homogeneity. Any point x, you should be in this, you should be equal. So there is no difference in the distribution function if I am here or if I am somewhere else. So this means that in this case, the Liouville operator reduces to the following form. You have a E d in dt. Sorry. Of course, modulus of p I can trade with the energy if I want. Okay? So in that sense, this is also a simplification. And therefore, I have the following d in de. Well, actually, this one comes from p0, so it's exactly a e. And this one I have to apply to my distribution function, and has to be equal to the collision integral. Now, there is usually a little bit different way to write it, because in some cases we would like to have the dependence not of the distribution function, but actually we don't care very much about the momentum dependence. We care about the number of particles. Okay? So it should be clear, therefore, that in principle we could take an integral in the 3p of the Liouville operator acting on my distribution function. Okay? If I do this integral divided to pi, of course, cubed, well, I have the computation, the particular computation. What you can do in that case, you can do some partial integration, and you can actually rewrite this as a derivative to the number function. So in practice, you can take the derivative in time out of the integral, and you will get dn in dt. And then you have again to do some partial integration of the second part, this p squared dE. And you can obtain out of it actually a plus 3h again n. Notice that in this case n depends only on t, of course, not on x, because I dropped the dependence on x. Okay? Well, I didn't do all the steps, but it's just a matter of doing some integration and partial integration in the integral with this operator in order to get back the number density. Okay, so let me now consider the case. So it should be clear, therefore, that, for example, we could have the case where the collision integral is 0. Okay? Collision integral is 0, then I would have exactly dn dt plus 3hn equal to 0. Then you see that this is nothing else than telling me that the number density will be diluted like the volume. Okay? It will go again like 1 over a cubed, which is actually what I would expect, because the number density of particle should go down like the or 1 over the volume. Okay? So this seems to be a pretty much good equation. But of course, what we would like to see is also what happens. And sorry, and I have another last comment. This Liouville operator for the distribution function with 0 collision integral, you can also use for propagating the CMB photons, okay, after the last scattering surface. Because after they do the last interaction in the last scattering surface, they don't interact anymore. So they have zero collision integral. And what you have to do is just to see how they move around the universe with solving the equation with the Liouville operator on the distribution function of photon is equal to 0. And this is actually what you do when you compute the CMB. Of course, you have also in that case to take into account not only the homogeneous part, but also the fluctuations around the homogeneous. This means that at the end, what you use is the original, okay, Liouville equation and not the simplified one. But let me come now to the case where we look instead of a particular particle. So the case we are interested in is the case where we have one particle going out of equilibrium and out of chemical equilibrium. So in that case, as I said, what I am interested in is the case where I have a particle. For example, the usual assumption is that is a particle which is stable, so you don't have to worry about decay. Of course, in principle, in the collision integral, you could have also a decay term in generic case. But assume that you have a stable particle. So let me call it chemical decoupling. So I have a particle X. I suppose it is also as a kind of conservation charge or whatever, so that it cannot decay. And the only process you can have, for example, changing the number of particles, you can have the annihilation of the particle with its either it's an antiparticle, or if even it could also be a Majorana particle and then its own antiparticle. And this goes to two other particles which are in thermal equilibrium. And this could be standard model particle, it can be other particle, but the important thing is these are in thermal equilibrium. And this particle at the beginning is also in thermal equilibrium, but we will see in a minute it doesn't stay in thermal equilibrium forever. And then you can write the collision integral, because we know we have to consider these processes in the collision integral. And the collision integral takes the following form. You have a minus. You have to integrate over all the phase spaces of the other particles, okay, which are not x. So I have to integrate in the x bar, in the I and the j phase spaces. And these I will write in this funny form with a big pi. This is nothing else as d3p divided 2 pi, the two energies, and the usual, if you want, integral that you have in when you compute, for example, also a a scattering, a cross section. You have then, of course, a delta function which ensures the energy and momentum conservation. So you have that the momentum of px plus the momentum of px bar minus the momenta, sorry, this is a d4, so there is no arrow. So this is the global delta function which ensures momentum conservation in the process. And then, of course, you have, well, let me write it here. Is it a problem if I really write it here? It's just one line? So you have the matrix element for the process. Okay? And then, of course, I will have the distribution functions of the initial state. So, of course, this will depend on the how many particles I have the initial state. So the distribution particle of x, the distribution particle of x bar, and it will be, in principle, could be suppressed or enhanced by the final state distribution functions. So depending if the final particles are boson or fermions, you could expect, in principle, this factor 1 plus or minus fi fj. Okay, so here the plus sign is in the case you have a boson, and then you have an enhancement of the production. If you have a minus sign, is a fermion, and then you have a blocking, Pauli blocking, in case you have already a particle in the same practically element of the phase space. Now, of course, this is the process going in one direction. I have to do the same thing for the process in the opposite direction. So I have also the opposite. Which is, of course, coming. This is a minus sign here, because here I'm losing particles. I am annihilating x particle. Then I will have a term with a plus where I have producing the pi particles. In this case, the initial state are I and j. And I have again the delta function, which will be more or less the same. We say, and then I have again the matrix element, in this case for the inverse process, times the distribution function, in this case, of the initial state. So I have fi fj, and I would have the suppression or enhancement for the x and x bar particles. Okay? And this one is the collision integral with two terms. As I said, the 2p, the 2 pi thing is just nothing else as the number of degrees of freedom of the particle, the 3 momenta divided 2 pi cube, the 2 times the energy of the particle. And this is the invariant volume element that you usually use in the integration. Now, this would be what I have to compute, and in principle I could try to compute it. Of course, I can put in quite a number of simplification. Well, one simplification I can take is, of course, that there is no CP violation or T reversal violation. This would mean that this matrix element for the process in XX bar going to IJ is exactly the same as the process which goes in the opposite direction. Okay? So that would be, so simplify the thing. So one assumption is CP conservation. And this gives me the same matrix element. Okay? Of course, I can relax these assumptions, and indeed this is usually done if you want to do, for example, leptogenesis. Then you have to take track to the fact that the two matrix elements are not the same. And then it would be, as I said, the contribution will come exactly by the difference. But in this case, let's not violate CP. Then the other assumption is, I already said it here, I assume that E and J are in thermal equilibrium. This means that here, wherever I have this, the distribution of E and J, I can write equilibrium. Okay? So Fij is equal Fij equilibrium.
So if you don't assume equilibrium, then that equation was perfect. You just don't assume equilibrium.
Well, then of course I cannot close the equation in some sense, because I would need to have to know what the f's are, or to solve the equation for the f's, for the fi and fj.
Right.
Okay, so then I would have, for example, a system of equation for all f's, and then I would have to solve a coupled equation. But in this case, I said, if I assume that these are in equilibrium, I know the shape of them, and I don't need to solve for them. I can just plug them in. Okay? The other assumption is, again, the assumption of dilution, which we have already seen. The assumption of dilution allows me to drop the f's here in the final state, so I forget about the plus or minus f. And also allows me to take, instead of the Bose-Einstein and Fermi-Dirac distribution, actually the Boltzmann distribution for the f's, which also simplifies my life. So these would be the three. Yes? Question? No. The assumption of dilution. So this means that the f's are Maxwell-Boltzmann. And I can drop them everywhere. So here I can drop it, and here I can drop it. Of course, I can assume the dilution also not only of fi, but also of fx and all f's. So I assume for all f's that I can approximate with the Boltzmann distribution. Yes?
The collision term, those should be modulus squares.
Yes. So the matrix element, of course, is a modulus squared. Yes, sorry. Yeah. Okay, now of course there is another approximation one can do, and this approximation is assuming again that you have only chemical decoupling and not kinetic decoupling. What would that mean? This means that I can actually I know how the dependence of the momentum look like, even if I don't know what is the number of particles. So this means that I can assume if it is kinetic equilibrium. So that was the fourth assumption, kinetic equilibrium. This means that even if I don't know what fx is, okay, I know that it must be proportional to the equilibrium distribution, in the sense that the shape in momentum is exactly the same. So this is, you can write it in principle, often it is written like nx over nx equilibrium times f equilibrium. As you see immediately here, this means that the number density is not the equilibrium number density. So if you want, the overall normalization of the distribution function will be different, but the shape in momentum is the same. So you have the same Boltzmann suppression, even if you don't have the same number of particles. And these I will assume both for x and x bar. And this, of course, if you want the shape in the momentum distribution to be the same, it means that you have processes, for example, also elastic processes or other type of processes, which don't change the number of particles, but they keep the particle with the proper thermal distribution in the momentum. Okay, so this one actually is a very, very nice simplification. Why? Because then in principle I know all the shape of the distribution, and I can actually do the integral, okay? Because I know the dependence on p. The only thing I don't know is the overall factor, which depends only on time, okay? So this is a big simplification. So this means that if I can assume this, I can again go back to the integrated Boltzmann equation, which would be, if you want, the first moment also called of the Boltzmann equation, where you just integrate the Eluvian operator, and you integrate also the collision integral. This is nothing else as adding an integral in the phase space also of the x particle, which we are not integrating on here. And therefore, then you have practically, you can write the equation as a, dn in dt plus 3h nx is equal to here you have a integrated collision integral, so I can write it as a minus. I have the integral in pi x, the integral in pi x bar, the integral in Here you have to be a bit careful with the degrees of freedom, but I don't have time to spend on it very much, but you have just to keep track of. Then you have the delta function. You have the matrix element, which is the same for both processes, so I don't specify the process, it's just m squared. And then I have the difference in the distribution function. I have x fx bar minus, which here I can write as the equilibrium one, times nx over n equilibrium minus the fi and fj, which are also in equilibrium. Now, if you take the Boltzmann distribution for the f's, the product of fi and fj is actually equal to the product of fx x bar, because the momenta are the same. So the sum of the two pi pj is equal to the sum of px px bar. So if you want, if you want energy conservation, so the energy of the final state is equal to the energy of the initial state. And of course, if you write this as a Boltzmann distribution, this is nothing else as minus beta ex plus ex bar. Okay? And this one is the same as the here, the e to the minus beta ei plus ej due to the delta function. This means I can take out this factor. I can take out generically a factor of e to the minus beta e. I can take also ex plus ex bar. And I arrive to this one. Now, this again, you can simplify it just noticing that if you integrate in the final state, this one with the matrix element, this is nothing else as the usual cross-section. Okay? You integrate in the final state phase space with the delta function matrix element, this is sigma. So I can just drop this. And this is nothing else as a sigma for okay? Well, not really, actually. It's a sigma up to a velocity, because here you're not dividing by the usually flux factor, so it's actually a sigma v, okay, with the relative velocity between the two particles. And then this factor here does not depend on momentum, because here the number density depends only on time, so I can take it out, okay? So I have at the end here I have this is nothing else as a kind of thermal average of the cross-section on the initial state. And practically it's the definition. I can actually also extract this n equilibrium and define it as the average sigma v on the temperature beta. And then I have the factor of nx bar minus 1. Sorry, minus equilibrium, sorry. Then it's, of course, I took away the nx equilibrium. Okay? And this is usually the final equation that is used for chemical decoupling. You see immediately that in equilibrium you get zero collision integral, or you should expect to have. So as long as the nx follow the equilibrium, then this term is zero, and you just have the normal dilution of the density of the universe due to the expansion of the universe. But as soon as these are start to be or if you want, as soon as the cross section here is not strong enough to keep up the equilibrium, then in principle you can have a deviation, and then you can have a different behavior with respect to the temperature. Now, I had planned to rewrite this equation as a function of temperature, but I see that I am already at the end of the lecture. So I will probably just write it. So there are a couple of two other simplifications you can do. One is using exactly the entropy as a normalization of the densities, of the number density, because we saw that the entropy dilutes exactly as this part, okay? So if you divide the two, you get something which is not diluted anymore. So we can define a quantity which is usually much more useful, which is the abundance, also called often. It's calling y of t. And this is nothing else as the number density of the particle divided by the entropy density. Okay? Now, as I said, if you are in thermal equilibrium and then the collision integral is 0, then the scaling of an x is the same as the scaling of the entropy, so the dilution is the same. This means this quantity is constant. Okay? So that's the advantage. In thermal equilibrium, this is constant. If you are in thermal equilibrium and relativistic regime. Of course, as soon as the particle x becomes non-relativistic, then again the number density of the particle drops. Here I'm not writing the entropy density, of course, of the particle x. Here I'm writing the total entropy density. So this will actually instead go down pretty quickly. So if you have the plot, the dependence on y will be constant at the beginning when you are relativistic. It will drop down where you have the exponential suppression due to the Boltzmann equation when the temperature becomes, this is usually written as a function of m over temperature, where x gets of order 1, you start to feel the fact that the particle is non-relativistic, the number density drops, and this is the behavior of yx in equilibrium. But what is the dependence instead that you can solve? And okay, let me write the equation for yx in the variable x, which is m over t. And this is again another change of variable you can do using the Hubble parameter. Let me get to that in 1 second, and then I will be finished. And then the equation for this is has only a factor. Here there are some numerical factors that you probably don't care very much, which depends on the scaling with the entropy. So you have a 10 over g rho, which comes from the Hubble. You have a Planck scale, which comes also from the Hubble, the mass of the particle. And then you have exactly these average of the cross section, and then you have a y square or yx bar minus yx by equilibrium yx bar equilibrium. Okay? So this is the form of the equation, and this is a little bit more simple to see the solution. I will just tell you what the solution is probably most of you already know. It's again, as long as you have a sigma which is very efficient, then it's clear that the only way to have a constant solution is to have the number density equal to the equilibrium number density. And this will be actually the beginning. You start following the equilibrium. But then at a certain time, sigma, actually here it's a bit hidden, but this one is a factor of 1 over h, okay, the Hubble parameter. So you are comparing again cross-section to the Hubble parameter, and at a certain point, if the cross-section is not strong enough with respect to the Hubble, or is much smaller than the Hubble, this term will become small, and you're not able to keep the thermal equilibrium anymore. And in that case, then, this drops out. And it drops to a constant again, because then this part will go to 0, and then you have again the same dilution as the entropy. This is the advantage of this quantity. Y, it starts as a constant, and it ends up in as a constant, and it has an evolution only in a relatively finite range of temperatures. Okay? Now, how is the final value? If you do the computation, which I was planning to do, but I will not, you find that the final y, if you want, so at x final, tend to go like 1 over sigma v. Okay? And this is actually pretty natural, because the stronger is sigma, the longer you stay in thermal equilibrium, and the smaller you become here. And instead, the larger is sigma v, sorry, the smaller is sigma v, the earlier you decouple, and the larger is the number density. And this is the famous WIMP miracle. So if you want to have the right ballpark of omega h square order 1, you better choose a cross-section which is similar to the electroweak cross-section. So a mass of 100 GeV and an alpha of order 100 0.1 or something like that works pretty fine. And this in some sense is one possibility. And as I said, in this case, you practically have to fix the cross-section and you get out the number density of the particle. Okay. What else wanted to say? Well, I mean, of course, it should be clear that I can use, of course, the Boltzmann equation also for other cases. In particular, for example, nowadays there are other possibilities. You could start not in thermal equilibrium. You could have particles which, instead of depending on 2 to 2 processes, they depend from T to 2 to 3 processes. And then, of course, you have to complicate your collision integral and take into account 2 to 3 processes. Moreover, of course, you could have a decay in principle. If the decay is low enough, it does actually not change very much this decoupling, but it will at a certain point. For example, it could give you either the decay of the particle today or the decay of the particle after it has decoupled. Okay? So you can play around with different models and different type of particles, and in some sense generalize this WIMP picture or this Boltzmann equation based discussion to many different scenarios. Moreover, as I said, also in this case I was taking mostly the equilibrium particle to be standard model particle, but it should be clear that this is also true from any other sector you would like to consider. And there are also possibilities to have a hidden sector with its own temperature and the standard model sector with another temperature, and they can be, for example, for a certain epoch of the universe also decoupled from each other. Okay, and you can do the same computation, you only have to keep track the difference in temperature and to see when they are in equilibrium and when not. Okay, I think we all want to go to lunch, and I am really sorry that I had to rush at the end. Unfortunately, I spent too much time on inflation, I guess. So I apologize because that was not my original plan. But anyway, if you have additional questions, of course, we can discuss them now or also during lunch. And and also I will be here this afternoon for a few hours, so probably until the end of the coffee break. So if you need, we can also discuss there. Yes?
So basically, this relation is the follows from this relation.
Yes, is this equation written as a function of the variable y, and from the variable y as a function of the variable x, which is the mass over the temperature. And of course, I am using the relation between temperature and time, which I obtained from the Hubble parameter. If you remember, I had Hubble of t, which is something like proportional to t squared. This is equal also of 1 over 2t time. One is t temperature and 1 is time.
So we are using this is only during radiation dominated.
Yes, yes. Here I am assuming I am during radiation dominance. Otherwise, of course, I would not, or at least the entropy density here would not be a very interesting quantity. Of course, I could use then the photon entropy density in case, but in some sense, I am during radiation dominance. If you would, you could in principle write the same equation during matter dominance, but then of course the relation would change. Because you have a different, well, the h goes always like 1 over t, but the dependence will not be on the temperature anymore, so you cannot really use the temperature as a variable anymore. Okay, I don't see any other questions, so we can close here.